Now let us see what happens if I consider the practical components. So when L and C both are ideal, there is no loss of energy, and whatever was the initial energy present with the capacitor, it remains throughout this generation of the sinusoidal signal. Whenever the transfer of energy takes place from capacitor to inductor and inductor to capacitor, there is no loss of energy because both L and C are ideal components. But we cannot have ideal components in practice, and hence any tank circuit, even if it just has capacitor and inductor, will always have non-zero resistance present in the circuit. That is nothing but the internal resistance of inductor and resistance of capacitor. And hence, even with the pure LNC components, there will still be the non-zero resistance present in the loop. And hence, in practice, any tank circuit, if you observe the voltage across capacitor or inductor, for example, you will see the charging and discharging. You will see the transfer of energy from capacitor to inductor and inductor to capacitor in the form of voltage waveform. But every time there's a transfer of energy, there is also the loss of energy in the form of power dissipation across the internal resistance. And hence, as you go from one cycle to the second cycle, in case of practical tank circuit, every time the amplitude will keep on reducing. So if you consider any practical circuit and if you observe the voltage across capacitor or inductor, you will get the sinusoidal oscillation, but you will see that the sinusoidal oscillations will be of reduced amplitude. So after a point of time, the sinusoidal oscillations will decay to zero. Please note that the waveforms are not drawn to the scale, especially in terms of the frequencies that we are showing. The frequency of the second waveform is shown to be greater than the first waveform, which will not be the case otherwise, right? So all we need to right now understand is that in any practical tank circuit, the amplitude of the signal will keep on reducing, and after a point of time the voltage across both the components will go down to zero. Now I want to generate something called as sustained oscillations. The sustained oscillations are those in which the peak amplitude of the oscillations remains constant. What I have shown in the second waveform is called damped oscillation. To convert damped oscillation into the sustained oscillation, all I should be doing is somehow compensate for this loss of energy which is taking place in every cycle. Then instead of amplitude reducing in every cycle, it will be exactly same as the amplitude in the previous cycle. And if I can compensate for the loss in every cycle, then I will obtain constant amplitude sinusoidal signal. So to do that, in every cycle we will apply the external current pulses of constant amplitude. So if I apply external current pulses of constant amplitude to the tank circuit, let us see what is going to be my response. Initially, I will generate the first cycle. Now, in the absence of the current pulses, the second cycle will be of reduced amplitude. But because I'm providing the external current pulse, the reduction in the energy from one cycle to the second cycle will be compensated by this external energy, and the amplitude in the second cycle will not reduce. So it is as good as generating first cycle again. Now, if you do not apply any current pulse, then again the oscillations will start reducing in the amplitude, but with the presence of the same equal energy current pulse, the amplitude of sinusoidal signal will again be of constant value. So the conclusion which we'll be using in the generation of DSB-FC signal is that if I give constant current pulses to the tank circuit, then I can generate the sustained oscillation. This whole feature of tank circuit is called flywheel effect. So what is flywheel effect? It is nothing but the generation of sustained oscillation in the tank circuit on the application of external current pulses, which account for the loss of energy taking place from every cycle to the next cycle.